everyone. It's nice to have you watching our show. I'm Jessie Nicole Pasahon.
I'm John Redo Tinawi.
And I'm Cristela Pusan. And welcome to
Be Smart Earth,
the show that brings you science-based facts and knowledge
about phenomenons, origins, theories.
And anything about our planet Earth.
In this episode, we will be having a rundown through various topics and try to have a deep understanding about these concepts.
Rocks. There are many types of it. It can be found everywhere on our planet. It's the basic unit of which a solid Earth is composed and typically form recognizable and mappable volumes. These are commonly divided into three major classes according to the processes that resulted in their formation. For as long as the Earth has existed, various exogenic processes have helped shape the landscape of the planet.
For our first segment, let's learn how do rocks undergo weathering, how are the products of weathering carried away by erosion and deposited elsewhere, how do rocks and soil move downslope due to the direct action of gravity. Let's find out.
Give me the rock!
What the rock?
Rocks are solid masses of geological materials. These include individual mineral crystals, inorganic non-mineral solids like glass, broken pieces from other rocks, and even fossils. Rocks are grouped into three main categories based on how they form. First, igneous rocks. It forms when melted rock cools and solidifies. Second, sedimentary rocks. They are generated when fragments of other rocks are buried, compressed, and cemented together, or when minerals precipitate from solution either directly or with the help of an organism. And lastly, metamorphic rocks. They are made when heat and pressure alter a pre-existing rock. Although temperatures can be very high, metamorphism does not involve melting of the rock. A mineral's chemical composition and inner atomic structure affect its physical characteristics. Numerous physical properties of minerals such as their color, crystal form, hardness, luster, density, and cleavage may be tested with varied degrees of ease. Numerous minerals also have unique properties such as radioactivity, black-like fluorescent, or acid reactivity. There are geological phenomena and processes that originated externally to the Earth's surface. These are called exogenic processes. They are genetically related to the atmosphere, hydrosphere, and biosphere, and therefore processes of weathering, erosion, and etc. Let's tackle each process. Weathering is the process by which surface and subsurface rocks disintegrate, dissolve, and are broken down. Rocks at or near Earth's surface are exposed to physical and chemical weathering processes. In the process of weathering, the Earth's surface gets broken down, helps in shaping the landscape, and wears away rocks and soil. The process of weathering typically begins when the Earth's crust is uplifted by tectonic forces. After the physical breakup and chemical decay of exposed rocks by weathering, the loosened rock fragments and alteration products are carried away through the process of erosion. The next process, erosion. Erosion is the process by which natural forces move weathered rock and soil from one place to another. Mass movement is an erosional process that moves rocks and sediments downslope due to the force of gravity. The material is transported from higher elevations to lower elevations, where other transporting agents like streams or glaciers can pick it up and move to even lower elevations. Next, transport by wind. Wind transport can result in stunning landscapes as sand is blown away from one place to another. In deserts, dunes are created. Wind can also create sandstorms and destroy farms by blowing away the topsoil of large farms. Gravity facilitates the downslope transportation of loosened weathered materials and enables them to move without the aid of water, wind, or ice. Gravity-related erosion is a major component of mass wasting events. And that's all. Back to you guys.
Thank you for that, Jessie.
Our next segment talks about why the Earth's interior is hot.
And we'll describe the formation of magma and what happens after magma is formed. Let's watch this.
Hey, have you ever wondered how hot it is underneath the ground you are stepping on? What do you think, partner?
I thought so too. It is said that the heat from when the planet originated and the heat from radioactive element decay are the two primary causes of the extremely heated interior of the Earth that exceeds over 5,000 degrees Celsius.
You're right about that. In fact, the decay of radioactive materials is the primary source of heat. Unstable elements like uranium-238 or potassium-40 stabilize with time and create what are known as daughter products lead-206 for rhenium and argon-40 for potassium. Radioactive decay is a natural process. About 90% of the heat produced by the Earth's internal process is heat.
That's right. But did you know that there is a common misconception that magma and lava are just the same? But in reality, there's a difference between the two.
What are their differences?
Under the Earth's surface, there is a combination of rocks called magma that is both molten and semi-molten. This combination typically consists of four components: a heated liquid-based substance known as the melt, minerals that the melt crystallized, solid rocks that the melt mixed with from the surrounding constraints, and dissolved gases.
Lava is the substance that is expelled from a volcano or other vent when magma is present. Igneous rocks is formed when magma solidifies after cooling. The temperature of magma ranges from 700 to 1300 degrees. Can you imagine that? Magma is an extremely fluid and dynamic material that may participate in physical and chemical changes in a number of different situations thanks to the heat it generates.
You're right about that. The existence of magma is essential to understand the geology and morphology of the mantle because the majority of the mantle and the crust are solid. Different types of magma form as a result of variations in the mantle and crust's structural features, pressure, and temperature. The mainly solid mantle of the Earth rises as a result of decompression melting. Convection causes this heated material to ascend to a place with lower pressure. Always, regions with less pressure have melting points that are lower than those with more pressure. The mantle rock may melt and produce magma thanks to this decrease in the pressure above it. known as decompression.
The buoyant magma below rises and fills the area of decreased pressure as a result of the rifting action. After cooling, the rock forms a new crust. Mantle plumes, columns of heated rock that ascend from the Earth's high-pressure core to its lower-pressure crust, are another location where decompression melting takes place. These plumes sometimes are called hotspots. When they are found beneath the water, pours magma into the bottom. Over millions of years of activity, these volcanic mounds might develop into volcanic islands.
The heat from the liquid rock is transferred to the crust when it solidifies. At convergent borders, when tectonic plates are colliding, heat transfer frequently takes place. Hot rock from below may intrude into the colder plate above. When the denser tectonic plate subducts or sinks below the less dense tectonic plate, this procedure generates magma while transferring heat. The magma in the subduction zone has the ability to form a volcanic arc, a group of active volcanoes.
Wow, that's really amazing. Back to you, Jesse.
It's getting hot in here!
It sure is getting hot in there. I wish I had a dream like that too. I'm so jealous.
Moving on, we see rocks in our daily life. We notice their differences in textures and mineral components.
I'm sure that once in your life you have thought about how it happens. Are temperatures and pressure factors in it? Let's find out.
Is this stress? Or this? How about this? Or maybe this?
First, let's discuss the process that refers to the changes in mineral assemblage and texture that result from subjecting a rock to pressures and temperatures different from those under which the rock was originally formed. Do you have any idea of it? It contains the words meta, which refers to after, and morph, which refers to form. When combined, it is after form. If you guessed metamorphism, then you're right! During metamorphism, a rock undergoes changes in texture and mineralogy. These changes take place mostly in the solid state and are caused by changes in physical or chemical conditions, which in turn can be caused by such things as burial, tectonic stress, heating by magma, or interactions with fluids. Protolith, or the original rock that has undergone metamorphism, can be any type of rock, and sometimes the changes are so dramatic that it is difficult to tell what kind of rock it was originally. Metamorphism therefore occurs at temperatures and pressures higher than 200 degrees Celsius and 300 megapascals. Rocks can be subjected to these higher temperatures and pressures as they become buried deeper in the earth. Such burial usually takes place as a result of tectonic processes such as continental collisions or subduction. The upper limit of metamorphism occurs at the pressure and temperature of wet partial melting of the rock in question. Once melting begins, the process changes to an igneous process rather than a metamorphic process. Pressure increases with the depth of burial, thus, both pressure and temperature will vary with the depth of the earth. Pressure is defined as a force acting equally from all directions. It is a type of stress called hydrostatic stress or uniform stress. If the stress is not equal in all directions, then the stress is called differential stress. There are two kinds of differential stress. Normal stress causes objects to be compressed in the direction of maximum principal stress and extended in the direction of minimal stress. If differential stress is present during metamorphism, it can have a profound effect on the texture of the rock. Shear stress causes objects to be smeared out in the direction of applied stress. Differential stress acting on rocks can have a profound effect on the appearance or texture of the rock. Rounded grains can become flattened in the direction of maximum stress. Minerals that crystallize or grow in a differential stress field can have a preferred orientation. This is especially true of sheet silicate minerals. Example is the micas, the biotite, muscovite, chlorite, talc, and serpentine. These sheet silicates will grow with their sheets oriented perpendicular to the direction of the maximum stress. The preferred orientation of sheet silicates causes rocks to easily broke along approximately parallel sheets, such as a structure called a foliation. Let's now move on to how rocks behave under different types of stress, such as compression, pulling apart, and shearing. First is compression. Compression stress squeezes rocks together. The compression causes rocks to fall or fracture. Example is when two cars collide, compression causes them to crumple. It is the most common stress at convergent plate boundaries. Second is pulling apart. Tension stress pulls rocks apart. It causes rocks to lengthen or break apart. Tension is the major type of stress found at divergent plate boundaries. The last one is shearing. Shear stress happens when forces slide past each other in opposite directions. This is the most common stress found at transform plate boundaries. Confining stress comes from the weight of all the overlying rock. This weight pushes down on a deeply buried rock. The rock is being pushed in from all sides, which compresses it. The rock will not deform because there is no place for it to move. Let's have a simple demonstration about the three types of stress. Take it away, guys!
Good day, everyone! Today, we are going to show you a simple demonstration.
About three types of stress using edible models.
For the first model, we have compression.
Compression is a stress that decreases the volume of a material. For our second model, we have tension.
It is a stress that pulls the materials apart.
And for the third model, finally, we have shear.
Shear is a stress that causes a material to twist. Thank you so much for joining us in our simple experiment. Back to you guys!
What an amazing demonstration! I'm sure that our viewers can now understand the three types of stress using simple materials at home.
For our fourth segment, we will go through the layers of the Earth.
And dig for the evidences that support the continental drift theory.
Pizza crust. Crushing on someone else. Crushing of glasses.
But legend says crust is.
Just like cakes, the Earth has layers too. Let's talk about that. The crust is everything we can see and study directly. The thinnest layer of the Earth crust still measures about 40 kilometers on average, ranging from 5 to 70 kilometers or 3 to 44 miles in depth. But on the scale of the planet, that's less than the skin of an apple.
Did you know that there are two types of crust? The continental and oceanic crust. The oceanic crust can be found at the bottom of the oceans or below the continental crust. It is generally harder and deeper, consisting of denser rocks like basalt.
While the continental crust contains granite-type rocks and sediments, the continental crust is thicker on mud.
Next is the mantle. The mantle extends down 2,890 kilometers, making it the thickest layer of the Earth. It makes up about 84% of Earth's volume. The mantle is also divided into several layers based on seismologic properties. The upper mantle extends from where the crust ends to about 670 kilometers. Even though this area is regarded as spacious, you can also consider it as formed from rock. A rock called peridotite to be more precise. Below that, the lower mantle extends from 670 to almost 2,800 kilometers below the surface. It is now generally acknowledged that the mantle is in continual motion rather than a steady state. There is a broad convective circulation with warmer material moving deeper and hotter upwelling towards the surface. It is generally accepted that this convective controls the movement of plate tectonics within the crust.
Next to mantle is the core. The solid inner core has a radius of 1,220 kilometers, while the liquid outer core extends up to a radius of 3,400 kilometers. Like the mantle, it is also divided into two layers.
Then we have the outer core. The hottest part of the outer core is actually hotter than the inner core. Temperatures can reach 6,000 degrees Celsius, as hot as the surface of the sun. It's a low viscosity fluid, making the name liquid very misleading. It is pliable and easily distorted since it has a very low viscosity. There is intense convection there. Additionally, it is believed to have extremely ferocious convection currents. The Earth's magnetic field is caused by the outer core's churning and its relative movement.
Lastly, the inner core. The temperature and pressures of the inner core are absolutely extreme, at approximately 5,400 degrees Celsius and 330 to 360 gigapascals. These plates are not stationary but are in relative motion to one another. The inner core of the Earth is thought to be growing very slowly, and this has a significant impact on the generation of the Earth's magnetic field.
There are three types of plate boundaries depending on geologic setting: convergent, divergent, and transform. These plates float on the soft plastic upper mantle. They are moving away or towards one another.
Now, let's talk about the evidences for continental drift. Evidence number 1. Identical rocks of the same type and age are found on both sides of the Atlantic Ocean. Wechsner said the rocks had formed side by side and that the land had since moved apart.
Evidence 2. Mountain ranges with the same rock type, structure, and ages are now on opposite sides of the Atlantic Ocean. The Appalachians of the eastern United States and Canada, for example, are just like the mountain ranges in eastern Greenland, Ireland, Great Britain, and Norway. Wechsner concluded that they formed as a single mountain range that was separated as a continent's drifter.
For evidence 3, ancient fossils of the same species of extinct plants and animals are found in rocks of the same age but on continents that are now widely separated. Wechsner proposed that the organisms had lived side by side, but the land had moved apart after they were dead and fossilized. He suggested that the organisms would not have been able to travel across the oceans.
Now for evidence 4, grooves and rocks deposits left by ancient glaciers are found today on different continents very close to the equator. This would indicate that the glaciers either formed in the middle of the ocean and or covered most of the earth. Glaciers only develop today on land and closer to the poles. According to Wechsner, the continents shifted to their current location later after the glaciers centered over the southern landmass near the South Pole.
And for the last evidence, evidence number 5, coral reefs and coal-forming swamps are found in tropical and subtropical environments. But ancient coal seams and coral reefs are found in locations where it is much too cold today. Wechsner suggested that these creatures were alive in warm climate zones and that the fossil and coal later drifted to new locations on the continents.
Back to you guys!
Up until now, we haven't explored so much in the deep of the ocean. But thanks to the scientists and researchers, because they were still able to gather fascinating facts deep under the sea. Let's join Jezebel in her underwater adventure.
Baby, baby, you're my sun and moon. Girl, you're everything between. A lot of pretty faces could waste my time, but you're my dream girl. Oh, didn't see you there. I'm Jezebel. Come join me in my underwater adventure as we explore more about seafloor spreading. And we might encounter some of my friends too. Let's go! Did you know that the seafloor spreads? I know it sounds silly, but seafloor spreading occurs at divergent plate boundaries. It is when two oceanic plates move apart from each other. They cause cracks in the seafloor. This is called, again, seafloor spreading. The mantle's convection currents generate heat that makes the crust more flexible and less thick when tectonic plates slowly drift apart from one another. Less dense material rises, often creating mountains or raised seabed regions. The crust eventually cracks. Now, let's go to the ocean basins, or areas that are below sea level. It makes up about 70% of planet's surface. Most of the water on the planet is contained in these regions. In fact, keeping in mind that a basin is a large bowl, similar to your kitchen sink, will aid in your recall of this term. So, imagine an ocean basin as a huge bowl filled with water from the ocean. You might recognize some of the features of the ocean floors as being comparable to some terrestrial structures. Many of the basin's prominent features, such as the jag, linear fracture zones, deep sea trenches, and steep ocean ridges, vary from this average. Along with the seamounts and guyots, seismic ridges, abyssal hills, and other noteworthy features of the ocean floor are also present. Now, let me tell you about the evolution of ocean basins. The ocean basins have expanded and contracted over a period of 2 billion years while plate tectonics has occurred on Earth. The supercontinent Pangaea, the huge landmass that included almost all the current continents, broke up slightly about 200 million years ago, marking the beginning of the most recent episode of ocean basin growth. Since then, there have significant several changes, such as the Pacific Ocean's contraction at the expense of the Atlantic and Arctic Ocean's expansion, the opening and closing of the Seaway, which circles the globe in tropical latitudes, and the opening of the Southern Ocean as the southern continents migrated northward away from Antarctica. The arrangement of ridges and plates that persisted for an undetermined period of time gave rise to the Pacific Ocean floor at this location during seafloor spreading. It involved at least 5 separate seafloor spreading centers. The rifting of Africa and South America from Gondwana, a supercontinent mostly made up of the modern-day continents of the southern hemisphere, occurred between 165 and 145 million years ago, resulting in the formation of the oldest portion of seabed in the Indian Ocean. I forgot the next terms. Can you help me, guys?
Sure thing, Jezebel.
Me and Starla are glad to help you. After the formation of seabed in the Indian Ocean, South America, Eurasia, and North America were connected to Africa. The current location of this ancient seabed lies near to Queen Maud Land and Enderby Land in East Antarctica, from the Somali Basin to the east coast of South Africa. North America and Eurasia, which together made up the majority of the large northern continent of Laurasia, started to drift away from Africa and South America around 180 million years ago, forming the first seafloor in the central region of the North Atlantic and opening the Gulf of Mexico. As Europe separated from Africa during this rifting episode, the Tethys Seaway also opened.
Yup, that's right, Crowdo. And as far as I can remember, shortly after this, the Timor Sea's earliest seabed was formed when continental chunks, perhaps including Tibet, Myanmar of Burma, and Malaya, drifted away from Australia's northwest coast and moved north. Spreading in the Pacific Basin persisted at this time as a result of the expansion of the Pacific Plate and the subduction of several of its neighboring plates, including the Izanagi, Farallon, and Phoenix. During this time, and even now, the Pacific Plate was moving northward.
You have a good memory, huh? But let's not forget that In between 60 and 35 million years ago, the Philippine Sea's western seafloor began to form. Back arc spreading from 30 million years ago created it in the east. It's unclear where the older crust came from. It either arose from back arc spreading behind trenches to the south, or from spreading in the Pacific Basin and subsequent capture by the creation of the Bonin and Mariana arcs.
Thank you, my dear friends. Now, before I say my goodbyes, let me share with you how the movement of plates leads to formation of faults, trenches, volcanoes, reef valleys, and mountain ranges. When the plates move, they collide and stretch apart, allowing lava, a highly hot molten material, to emerge from the mantle. Then the collision results in the said geologic features. Thank you so much for joining me in my underwater adventure along with my friends. Back to you guys!
Thank you, Jezebel, for giving us a tour.
And that wraps up our Science Magazine show
This has been the show that brings you science-based facts and knowledge
about phenomenons, origins, theories,
And anything about our planet Earth. We hope you learned something today. We will see you on our next episode. Once again, this is
Be Smarter!